Welcome back to Arts Learning. In this video, we're going to go over how to put together the universal law of gravitation, centripetal force, as well as the force of charge, right? The electrostatic force. And we're going to learn how to solve questions that incorporate all of these, okay? Because it does get hard when you put a lot of them together. All right, so let's start. First, the first scenario is when gravitation is your centripetal force. And before I start, I just want to make sure that you know on artslearning.com, under the chapter for Unit 6, which includes the topics I just covered, there will be PDFs that cover more deep problems in this if you're looking for more practice and harder questions. These are just more conceptual on how to solve these. But there are problems as well. So this is what's used for planets, right? Because, for example, if you have, let's just say Earth, right? This is Earth. Looks a bit shabby for Earth, but just take it at face value. And this is the sun, right? What is keeping this Earth in orbit around the sun? We know that's a circular orbit, right? So it has to be a centripetal force. And what's the only force out in space? The force of gravity, right? So the G, big M, m over r squared, has to be equal to m times v squared over r, right? Because this is mass times acceleration centripetal, and we know acceleration centripetal is just this. And this is just force centripetal, right? Force is equal to mass times a. Since this gravitation is the entire net force here, we can equate it to mass times acceleration, right? So then we can solve for the velocity by multiplying, we can divide both sides by m first, then multiply by r, take the square root of that, and there you go, you have your velocity. So that's just one of the ways you can solve using this equation, okay? For planetary problems and planetary motion, which also includes centripetal motion. Then for the charge orbit, similarly, kq1, q2 over r squared is equal to mv squared over r. So this is for a rotating charge, okay, when a charge is orbiting another charge. So you might not see it a lot, but it does happen, right? And same thing, similar thing, you just v squared is equal to kq1, q2, and then one of the r's is canceled out. And then take the square root of that, and there you have your v. So that's another way you can be asked, okay? But the most concerning thing, and where I've seen students mess up a lot, is a vertical circle. So when I went over the last video, I talked to you about how horizontal circles need a vertical component of tension to balance out, right? But here, if you look at this, a vertical circle, right? Vertical circle means you're spinning it up and down. It's not like a hula hoop where it's a horizontal circle. Think of a vertical hula hoop, right? You're spinning it up and down like that. Or you're taking a yo-yo and you're spinning it up and down. All right? That's a vertical circle. And tension is your force there, right? Tension is your force. But also, tension is your centripetal force, but what other force is going to weigh you down here? The force of gravity, right? So suppose at this point, we'll have a force of gravity downwards, and our force of tension will also be downwards, right? Because we have to go downwards to here. So then if our tension was our total force centripetal, then that wouldn't make sense, right? Because we have a force of gravity as well. So it wouldn't be able to stay in orbit. So that's why we're going to have to incorporate gravity as well. And I'll show you how to do that coming up, okay? It works different at different points in the circle. Okay, so let's look at the vertical circle. Over here, you can see, suppose I was spinning it this way. It doesn't really matter which way I'm spinning it, okay? Just velocity is tangential. So it could be either that or that. But let's just say I'm spinning it the other way. So it's like this. Let me try drawing a better straight line. Okay. This is a velocity, so we know our force has to be like this, right? Perpendicular here. And this force, since it's a yo-yo, right? That's the force of tension. That's a centripetal force. But at this point, tension is pulling you downward, right? Because it's your centripetal force. It's trying to go inward to your circle. But also gravity is pulling you downward. So then tension can't be your entire centripetal force, right? Because then, since tension plus mg, it would be greater than your force centripetal, which means you would be out of orbit. So your tension plus mass gravity is equal to your force centripetal, because that's the scenario where it's under orbit, right? Because if tension itself was your force centripetal, then this would be a greater than force centripetal, and that would send you out of orbit. But if you want to stay in orbit, you have a certain force centripetal, and all the net forces must add up to that, right? Even when I was doing net force before, I showed you, right? Net force is equal to force centripetal. That's why I was able to use mass times acceleration centripetal. Otherwise, I wouldn't be able to use it. I know my net force is my force centripetal, right? So my force centripetal here is not just one of the forces, it could be both. So in this case, up here, that's the case, right? Because gravity is weighing us down. So tension plus mg is for force centripetal. And this depends, right? This mg, so I'll show you a crazy problem in a few minutes, or maybe next video. But mg here is imagining that you're on the Earth, right? But if your tension was, suppose you were out in space and you were swinging a yo-yo, and then there was a planet here with attraction, then you'd have to use the gm1 m2 squared over r squared. But that's for later, okay? That's a more complex problem. Now over here, so for now, just imagine everything's on Earth. Over here, what's this going to look like? That's just going to be, well, over here, so suppose I'm spinning it this way, my velocity is going to be tangential at that point. Our tension will pull us inward to this point here, okay? But what's going to pull us outward? mg is going to pull us downward here, right? So tension plus mg can't be our force centripetal anymore, because mg is actually pulling us downward this time. We're acting in a different direction, right? So if this was our force centripetal, that wouldn't make sense, because they're both going in different directions. So we have to compensate for that. So tension is going in a positive direction, right? It's attracting ourselves to the center. But mg is pulling us away from the center. So tension minus mg is going to be our force centripetal. So accordingly, you can kind of understand that tension has to be larger than mg, right? To give us a force centripetal. Otherwise, we wouldn't have a force centripetal. It would just be zero. So yeah, in this case, that'd be the case. So here tension has to be large, right? Here tension has to be low, because mg is helping it out. Here mg is hindering it. But there is a case in which mg doesn't do anything to it. So over here, you can see, so imagine the ball was over here, right? Tension will be pulling us inward. But what's pulling us downward? So gravity is over here. It doesn't do anything to our tension here, right? It just doesn't do anything here, because our tension is our centripetal force. And here, this mg isn't hindering it at all. It's actually the cause of the velocity here. Over here, it's inertia, but over here, its velocity is being caused by the mg, right? And even if I wanted to write an equation for this, I really can't, because tension is only one pulling us towards our center. This gravity isn't hindering or helping it, right? Because they're both in different components here. Tension is horizontal and mg is vertical. So at either of the sides, you don't need to worry about it. Okay, so at either of the sides, it's just the same. Same old tension is equal to force centripetal. At the top, tension has to be lesser than force centripetal. At the bottom, tension has to be greater than force centripetal to compensate for the gravity hindering it. All right, and then of course you can substitute in force centripetal with mv squared over r, and you can go along your way doing that. So now let's try a problem. So this is, we go over one of the vertical circle problems in a bit, but let's try one for orbital speed. Okay, a satellite orbits Earth, so Earth 5.97 times 10 to the 24 kgs, a lot of mass, right? At r is equal to 7 times 10 to the 6 meters. So our radius here would be 7 times 10 to the 6. Find its orbital speed. So that means we know that mv squared over r, that's our speed, right? Orbital speed. And that's our centripetal speed, orbital speed here, because it's centripetal motion, is equal to the force of gravity, right? Because the only force between the satellite and Earth is the force of gravity. Big G, big M, little m over r squared. And yeah, little m, we can denote that as a satellite because it's the little m, right? And big M is our Earth. So before solving for v, I can simplify this a bit. The mass here, the little mass doesn't matter at all. So we don't need the mass of the satellite. You might have originally gone ahead to kind of substitute it in, and you would have understood that it doesn't help you out, right? So always before you start substituting in stuff here, make sure that they don't cancel out. If they do cancel out, then, well, you have lesser stuff to deal with. So v squared, so v is just big G, big M over r, square root of that. So just square root of 6.67 times 10 to the negative 11, right? And then big M here. So big M 5.97 times, so I'm running out of space inside the bracket here, times 10 to the 24. All of that divided by 7 times 10 to the 6. Let me increase the bracket here. That should give you about 7.54 times 10 to the 3 meter per second. Okay, and if you're wondering what the units are here, G, the units of big G, because force is equal to big G times kilogram squared over meter squared, right? I went over this before, so if you don't understand it, that's fine. Just make sure to look at what I did. We know a Newton is a kilogram meter per second squared, right? So in order, the G has to multiply out these out to give us that. So it's a meter cubed, and then meter cubed, it's a kilogram. So meter cubed, kilogram, second squared. So weird units, but just bear with it. Okay? All right, and then, yeah, let's keep going. So now let's look at a vertical circle. A vertical circle here, so similar here, right? It's going like that. It doesn't look like a circle from the way I drew it, but it is a circle. And this circle has 0.4 kg ball, right? A mass of 0.4 kgs here, a velocity of 5 meters per second. So that's just the speed here. Velocity keeps changing because it has a different direction. And a radius of 0.7 meters. So that's the string length, right? The length of the string is the radius. And now we need to find out the tension at the top and the bottom, because you understand how that's going to be different, right? Because I just showed you why that's different. So pause the video and give it a try yourself, and then I'll go over it. Okay, so I'm assuming you gave it a try. Let's look at it now. So here, right, we have the bottom is T is equal to mv squared over r plus mg, because we know that at the bottom, right, tension is the force pulling us upward here, minus mg, right? because that's the force pulling us downward. So it's pulling it downward here. And then that's going to be equal to our force centripetal, because that's our net force, right? And the force is giving us orbit here. Or in other words, m times v squared over r. So what I just did here was I just did tension. Let me actually label this as tension bottom, because the tensions are different in each scenario, right? Is equal to mv squared r plus mg. So you can substitute in here, right? 0.4 times 5 squared over 0.7 plus mg 0.4 times 9.8. And if you plug it in, it should give you about, let's see, 18.2 newtons. So tension bottom is 18.2 newtons. And now, if you keep this in track, right, we'll understand that the tension at top has to be lesser. I'll show you exactly why. Tension at bottom has to compensate for the force of gravity pulling it downward, right? It has to add extra force to keep it in orbit. But here, the tension at the top, right, tension at the top is assisted, because tension at the top is going downward, pulling towards the center, right? Mg is also pulling downward. So tension at the top plus mg, because they're both assisting each other, is the mass velocity squared over r, or a centripetal force. So tension at the top is just mv squared r minus mg, right? So it's about 0.4 times 25 again over 0.7, but this time minus mg. So 0.4 times 9.8, right? So about 10.4 newtons. There you go. So this makes sense. Tension at bottom has to compensate for the extra. Tension at top is actually aided by the extra, so it doesn't need to worry about all that. Yeah, that's it. If you wanted to find the tension at the sides, you could, right? You just need to go, tension is equal to mv squared over r, and then you can find the tension at the sides. Because at the sides, gravity doesn't have an effect. I just showed you why. And there you go, that's it. Next video we'll be covering, so we'll probably cover the PDF for this unit first, and then we'll cover unit 6.2, which has the same topics, right? Centripetal force, gravitation, and electric charges. But here we're going to be covering the fields between those, all right? So the fields between those and how the fields look like. And we'll go over how to draw fields, what they look like. Do they attract or repel? We'll go over all that. So stay tuned for that, and give me a like and subscribe if I helped you, so I can continue helping you as well as others. Thank you for watching.